Hello, this is Dr. Muhammad, and this is another video under Dynamics of Structures. Today we are going to talk about the forced vibration response to harmonic motion, undamped systems. Still we are under the same title that we have started last video, but today we are going to talk about some hints, so we are going to put it under the title part 2. So we are going to give some hints about the previous video, and we are going to talk about some important notes regarding the general equation of motion for our system. Okay, so we can put this, as I said, under some notes under the main general equation or main equation of motion, and we are going to give some important hints and notes to let us understand more about the general solution. Just a reminder of what we have explained last time, and it is only for you to remember that as I mentioned here, we were talking about the general solution, and we have two different types of or parts of this general solution: the complementary solution and the particular solution. And I said that this complementary solution, it has some characteristics. One major characteristic is it is depending on the initial condition, which represented here by these constants A and B, and in the same time it depends on the omega n of the structure of the system, means that the natural frequency of the system. As you can see, this part has nothing to do with the forcing frequency or the force that being applied in the system. So this is what we call it the complementary equation. And in the second part, we said, or in the second part of the solution, we call it the particular solution. We found that it is heavily dependent on the forcing frequency of the force that is being applied in the system, and in the same time P node, which is the amplitude of the force, and in the same time it depends on the structural stiffness and natural frequency. We put this as the general solution, and it is a little bit long, I know, but if you understand each part of it, you are going to get familiar with what we are going to explain. Okay, the first hint that I'm going to discuss, okay, is going to be related to the terms here, okay, as I have mentioned before. So let's write down, and this is, before going into the hints, this is the total response, as we have mentioned before. This is the total response, the solid line. However, the steady state response, it is the dashed line, and in between it is the transient response. Okay, so this is what we have explained already in the last video. Now let's go and try to write some equation, some notes. Okay. So note number 1, we can say in this equation, let's go and put let's assume that this equation is going to be equation 1, okay? Let's assume that it is, we're going to give it the title equation 1. So in equation 1, okay, in equation number 1, you're going to find, this is note and hint, you can't put it, okay, in your mind, the first and the second terms, okay, they gives oscillation at omega n, okay, these two terms give oscillation at omega n, means that at the natural period of the system, okay? Okay. However, the third term, okay, it gives, okay, the third term give the oscillation of, instead of omega n, it is going to be omega bar, okay? The same also, of not the system, but of the excitation, Okay, the excitation take care of this excitation. So we have like two different terms or two different parts. Each part has its own unique main parameters. So the first and the second terms, they are dependent on the natural frequency of the system. The third term, the third term is dependent on the on the frequency or the forcing frequency of the excitation. Okay, so this is, we can say this is the first hint. Okay. The second important hint that we need to write here, that the steady state, okay, response does not rely on the initial condition, does not rely on the initial conditions. That's very true, and we have explained about this before, which are like U node and V node. They are not going to rely, right? However, say this is however, it's very important. I cannot write here, I don't know why. However, the transient response does. The transient response does. It's very important, right? Because we have mentioned about this before, just I'm writing it down. As you can see here, we have U node, V node in the first and second term, right? And this is the transient term. However, in the steady state, we cannot see anything related to U node or V node, as I have explained in the previous video. Okay, note number 3, which is an important note also. The transient component is shown in the figure as the difference between the solid and dashed lines. As I have mentioned also, if we go back here, this part, which is the difference between the total response and the steady state response, this difference, we call it the transient. This is the transient, okay? This is the transient. This is related to this part. This is the transient, which is this equation here, the first two terms in this equation, okay? So this is an important thing that you need to keep in your mind. Okay, note number 4, which already I indicated last video, but I'm going to put it more clear here. It is the transient component, okay, is called like that. We're going to call it is called like that. What is the reason for calling it the transient here? As I said, because it depends on the structure omega n. Because it depends on the omega n, okay, omega n of the structure, right? Which will decay. That's the important point, decay, okay? Which will decay or vanish because of damping. Because of damping, it is going to decay or vanish. Okay? You are going to tell me that, well, we are talking now about undamped systems, so there is nothing related to damped system. Yes, that's true. But actually, as I said, what we are studying today is theoretical case. But the actual case, that damping is always going to be there. So we have called this transient component to be like transient because the damping going to make this component to vanish or decay. Okay? That's the reason for this name. Okay. Next, we are going to talk about the maximum static deformation or the static amplitude. Okay, which is 5. The maximum, we call it the maximum static deformation. The maximum static deformation. We call it static amplitude. Static amplitude. Okay. We are going to say that at any time, okay, the value of the static deformation, the value of the static deformation is going to be like this. U static, we're going to call it like this, U static, at any time t. That's the meaning of it. It is going to be P node, right? The force sine omega t, which is the force that we have over K, right? That's what we have. This is the static deformation at any point of time t, right? This is what we are going to do. This is the static deformation at any point of time t, right? Ignoring the dynamic, why we call this like the static deformation, and what is the meaning of static while that there is t is involved here? So it seems to be a little bit confusing. But actually no, you can assume it as like this, ignoring the dynamic term or dynamic effect in our main equation. In this equation, do you remember the main equation? mu double dot plus k u equals to p node sine omega bar t, right? Try to, like, we are going to neglect this part. What is going to be here? This is u. U here is what? If we are going to neglect the inertia and neglect the dynamic part, u is going to be the static one. Based on this, we can find that u, which is static, equal to p node sine omega bar t over k, which is here, this one, right? So that's the condition here. So we can say that u static equals to, sorry, can write down here, this is, put it in another. So we can say the maximum static deformation, the maximum, take care of the word maximum, static deformation is going to be what? If we say this is the value of the static deformation at any time, P node over K sine omega bar t. So this means that our maximum static deformation, which is going to be denoted, let's put it like U static only, it is going to equal what? If this term sine omega bar t equal to 1, then we are going to obtain P node over K. This is the amplitude here, the maximum. So it is going to be P node over K. Take care of this word again, maximum. So that no sign here, no sign something, already it is 1 because we are talking about the maximum. So this is what we call it, the maximum static deformation. The maximum static deformation. Okay, what is the main condition for obtaining this maximum static deformation? First of all, we're going to assume no dynamic effect, means that there is no inertia force. And number 2, that we are going to say that sine omega bar t of the this excitation, it is going to be 1, right? So that these are the main 2 conditions that we have. The main conditions. Okay? These are the main conditions that we have. Okay? Please remember that because really it is very important. Really it is very important. Okay? The maximum static deformation. Do not get confused. Do not get confused. We're talking about the maximum static deformation. So we started with what is the static deformation at any time. We said that U static at any time would equal to P node over K times sine omega bar over T, because the numerator here is the force and the denominator is the stiffness of the system. That's right. From where we got this equation, go back to the main differential equation, ignoring the dynamic effect because we want to obtain the static effect only. We want the static displacement. So we're going to say our dynamic or our differential equation is going to be mu double dot plus ku equal to p sine omega bar t, right? But we are going to neglect any dynamic effect because we want the static deformation. Then this term is going to be cancelled out. And we are going to remain with ku equal to p node sine omega t. This means that U static, which is this equation, P node equals to P node sine omega bar T over K. Okay, sorry for this. So this is the major or the main thing that we are having here. So based on this, we are going to have the maximum static deformation. The maximum static deformation as equal to P node over K. Okay? The 2 main conditions that we have is that we should neglect the dynamic effect in this case, and sine omega bar T equal to 1 means that we are picking the particular point of the force where that it is going to reach its amplitude. Okay? Okay. Now let's go to another point which is related to the note number, this is note number 6, okay? We're going to give it the title like this, which is omega bar versus omega n. What is the relation between the 2? Okay? So, first of all, in the steady state, let's go with the steady state. Okay? And in the steady state, okay, do you remember the steady state? We said that in the steady state, the equation, our equation is going to be U of t, means that the displacement at any time would equal to U static. Do you remember U static? Go back here, U static, P node over K, right? So U static times 1 here, 1 minus omega bar over omega n raised to the power 2, close the parentheses, times sine omega bar t, right? This is our equation. This is our equation. We are going to refer to it many times, so maybe we can say this is equation number 2. Okay, this is equation number 2. Okay. This part which is between the brackets here or this vertical square parenthesis, we can say that this part is going to be given a name. We are going to give it something called RD. So we are going to call it RD. This RD is going to be separated here, 1 over omega bar over omega n to the power 2, right? And we are going to give it this name, deformation response factor. Deformation response factor. This is what this RD is all about. It's a very important equation because we are going to find that repeatedly we are going to refer to it. Okay, repeatedly we want to refer to it. This is the deformation response factor. So this is only a deformation for kind of definitions for us. In the steady state, we found that this U static, which is, as I said, again, I'm going to put U static here so that you do not forget. It is going to be P node over K. Remember, will. It is the maximum static deformation. The maximum static deformation. Will. We are going to draw a relation between this RD and this ratio, omega bar over omega n. Take care, we are like focusing on the steady state part, which is the part of the equation that is going to go and like continue, okay? Even that we are undamped system, I know, but we want to focus on it in order to understand more about the relation between omega bar and omega n. So we have this plot, as you can see here. This plot is relating on the horizontal axis the relation between omega bar over omega n. And in the vertical axis, which is here, it is the value of our RD, which is here. This is the equation, which is RD. So the vertical axis, it is RD. Okay? From the equation here, if you are going to plot it, you're going to find that here it is 0, right? This means that if we're going to put when omega bar is going to be less than omega n, what will happen? This RD, our RD, is going to be positive, right? From the equation here, RD is going to be positive. Means that U of t and P of t means that the response and the force or the excitation is going to have the same sign. Okay, I'm going to talk about this in the next white page slide, so that I want to show it better for you. So we are going to say, let's assume that we have this here. If omega bar is smaller than omega n, this means that from our equation, RD is going to be what? Positive. What is the meaning of RD? We go back again here. RD, it is the deformation response factor. It is going to give us the relation, okay? It is going to give us the relation between the dynamic and static deformation. Okay, let's go here. So I want only to highlight, yes, here this is the static, as I said, this is the maximum static. This term here, or this parameter, it is the maximum static as we put it here. This is the, remember Will, it is the maximum static deformation, okay, the maximum static deformation. Okay, so if we have omega bar less than omega n, then RD is going to be positive based on the equation itself, based on the equation itself. This means that i.e., okay, that u of t and p of t, which means that the total response of the system and the excitation is going to have the same sign, have the same sign. Okay? That's right. This means that our system is going to be, we can call this is n phase condition. What is the meaning of n phase condition? This means that if we have the structure like this and the force being applied is in this direction, which is P of t, we are going to find that our system is going to be in the same direction, going to deform in the same direction of the force. So this is going to be u of t. Okay? Okay, that's good. That's good. And the important thing that our RD is positive. Positive means, go back again here. If omega bar less than omega n, this is omega bar over omega n. Here we have this is 1. So if it's less, this means that we are in this quarter. This means that RD is going to be positive, as you can see. It's the vertical axis. This is going to be larger than 0, of course. It is starting from 1, actually. Okay? So, or we can say that like ending or approaching 1 when omega bar over omega n reaches to 0. This means that we are in the positive part here. RD is positive. This means, positive part means that we are having the M phase condition. We are having the M phase condition. Okay, so the other part is going to be, or the other case is going to be if, let's have this, if omega bar is larger than omega n, what will happen here? In this case, RD is going to be negative, right? It is going to be negative. Let's go back to the relation. Yes, that's right. So here we are having omega bar over omega n. So omega bar over, larger than omega n. This means that RD is going to be negative, right? From the equation, because we are here. So we are going to be in this quarter. This means that RD is going to be less than 0, right? Here, this is the meaning of RD is negative. If RD is negative, then we're going to have U of t and P of t. They are going to be, we call it, they are going to have different sign. They are going to have different sign. What is the meaning of different sign? It means that they are going to be out of phase. Out of phase. Well, what is the meaning of out of phase? It is something like this. If we have the structure is going to be applied, the force being applied on it is going to be in this direction, P of t in this direction, then we're going to find the structure is going, because of the motion that he is under this motion, is going to deform like as if it goes in this direction, opposite of it. So here it is going to be U of t, which is the response of the system is going to be opposite to the applied force. You may think about it, or it is a little bit counterintuitive, but actually it is not. Under the motion, you're going to find at some level of the applied force, and at certain point on the motion itself, you are going to find that the applied force, when it is going to change with time, it will counteract the motion of the system itself. So this is the meaning of, as I said, the meaning of the out of phase motion. Out of phase motion. So remember, Will, they are coming from here. let's go back again to our, yes, let's go back again to our, like, our graph. So we are here in this part, so whenever that we have omega bar larger than omega n, so we are in this quarter, this means that RD is negative, and if you look here, you are going to find that our equation, the relation between the two, u of t and over u static, it is related to, or it has something to do with this factor, which is RD. So in this case, we are going to say that this factor is component or relation, like having the relation or like comprising the relation between ut and u of t, which is the dynamic response to the maximum static response. So sometimes it is positive, other times it is negative. Whenever it is positive means that we are in the end phase condition. Whenever it is negative means that we are out of phase condition. Okay. So let's go to maybe an important thing here, which is related to another understanding for the graph that we have here. Yes. So we have another important thing also, maybe this is the, we can say this is like note 7, for example. Okay. So in this note, first we want to highlight, okay, the relation between the, what is RD is all about. RD is going to be having the relation between the amplitude of the dynamic force, and it is going to be the relation between the dynamic displacement with the static displacement. Let's put it like this, the mathematical description, let's put it like this, the mathematical description okay of, let me like erase this part now, I'm going to talk about it in a minute. Okay, the mathematical description of in phase, the meaning of M phase and out of phase. What is the mathematical description of it? Okay, so equation number 2, let's go back here and say this is equation number 2. Yes, we mentioned about it. This is equation number 2. Equation number 2 can be rewritten as follow. We can say that u of t equals to u static, which is the maximum static displacement, times RD absolute, because we have this 1 over 1 minus omega bar over omega n squared, times sine omega bar n, omega bar t, minus something that we're going to add called phi. Okay, this is the angle which is representing the phase and out of phase condition, and we can put this equation again in this form: rho, which is the amplitude, and then we're going to put sine omega bar t minus phi. Well, we're going to see some new things here. What is this rho? We're going to call it the dynamic amplitude. The dynamic amplitude of the response. This is the dynamic amplitude of the response. This is our response, and there is something here multiplied by sine, sinusoidal function. So this something here, it is going to be the dynamic amplitude. This means that rho is going to equal U static. Remember U static? It is the maximum static displacement times RD, and this is the absolute value here. Okay? So this means that we can write that RD, okay, RD would equal to rho over U static, right? And it equals to, as usual, as we know, 1 over 1 minus omega bar over omega n to the power 2. Okay? That's a very important equation that we need to keep in our mind. Okay? Why we want to keep it in our mind? Because it is really important to know what is the relation, what is RD is all about. Look here, RD equal to the dynamic amplitude over the maximum static amplitude or the maximum static displacement. That's the point. This is the meaning of R. So it gives us how much that the ratio between the dynamic amplitude and the static amplitude is. This is going to be given for us. This is going to be given for us by this ratio, which is RD. We call this RD. In industry, they are commonly called this RD as the dynamic amplification factor. Okay, the dynamic amplification factor. Okay, based on this understanding and these equations, we can go to the next hint, which is going to be related to what we have explained before. So it is going to be from the same figure that we have from this figure. Okay? We're going to find that when omega bar over omega n is going to be very small, means here, we are here, okay? It is going to be very small. It is going to be near to 0. What we are going to find? We're going to find RD equal to almost 1. This means that the force is going to be slowly varying, okay? Because RD, which is the ratio between the dynamic amplitude and the static maximum amplitude, they are going to be the same. Means that there is no effect on the damping, no effect of the dynamic force on the system. The system is responding as if it is static. Okay? This means that the dynamic amplification factor here, or the deformation response factor here, is going to be like equal to 1, reaching to 1. Okay? So we need to put this as hint. So in the figure, if, let me put it in another color here, yes. If omega bar over omega n is small, then this means that the force is slowly applied. Okay? This is, or slowly like varying. Consequently, this means that RD equal to 1. As I said here, go back here, RD is going to be 1. Okay? And based on this, we are going to find that the maximum dynamic amplitude almost equal to the maximum static displacement. They are going to be the same. So what does it mean here? This means, this is the important thing, I can put it here, this means that no dynamic amplification. Means that amplification. What is the meaning of that? It means that the system is not going to be amplified due to the dynamic or the excitation of the force. I mean that the system is not going to experience any amplification, because this amplitude, the dynamic one, equals to the static one. Okay, now what if the other case, this is omega bar over omega n, it is small. What if that our omega bar over omega n larger than certain value, 1.4, okay? Let's go to the curve and see. Yes, it is almost 1.4. This is 1.5 here, so we're talking about something here, okay, which is corresponding to 1 here, okay? We're going to find, starting from here on, what is going to happen for the RD, the vertical axis, which is RD. It is going to be, yes, less than -1. I mean that it is going to be between -1 and 0. This means that RD is going to be less than 1, right? So go here. This means that RD is going to be less than 1. So this means the force is rapidly varying. The force is rapidly varying. It is varying rapidly. Okay? This means that the dynamic amplitude is less than the static amplitude. The force is being applied rapidly to the point that the dynamic, I'm going to write this, the dynamic amplitude is less than the static amplitude. Okay? This is what we are going to have, which is this rho is going to be less than U static. Okay? Okay, that's very good. Let's go to the last thing, which is the case where that if, what if that omega bar equals to omega n? Yes, here what we call it resonance is going to take place. Resonance. And based on that, you are going to find that equation number 1 will not work, is not valid. In this case, equation number 1 is not valid. Do you remember equation number 1? I have mentioned about it. And that before, yes, this is equation number 1. This part, you're going to find, this is equation number 1, and you're going to find that 1 minus omega bar over omega n, it is going to be here 0. This means that infinity, so it will not work for us. The particular solution would not work for us. So we need to put another solution for our case. Okay, so the steady state equation should be changed in this case. So the steady state equation, okay, should be changed in this part, okay? And our mathematician friends, they put it for us. The equation is going to be like this. Take care of this. It is going to be minus p node over 2k omega n times t times cosine omega n t, okay? This is, the particular solution is going to be for this case. And this is, as we said before, this is okay for the special case where that omega bar equal to omega n, the resonance case. What is the most interesting part here? Exactly, t is going to be outside of the function. This means that we are going to find augmentation of t is outside of the sinusoidal function. This makes the amplification to be infinity increasing. That's important. So I say that this is outside of the cosine. This means that u, p of t is going to increase with the increase in t. Okay? Directly. Okay? So based on this, we are going to find the resonance case here. That's what we are going to find for this equation. This is what we are going to find for this equation, that you're going to find that the response is going to increase, okay, increase in a way that is increasing with time. This is, if we assume this is t over tn, and this is the amplitude, or the dynamic amplitude over the maximum static amplitude. As you can see, infinitely, it is going to go in this way, up and down, up and down. Okay? So that's what we meant by the response or resonance case. Okay, and this is actually what we want to end with, which is the resonance case. Maybe I uploaded on the system some resonance systems or maybe some resonance cases, you can find it even in the YouTube or whatever, Tacoma Nero's bridge. You are going to find it, Nero's bridge. Just write it like this, and I think that I have uploaded for you. You're going to find what is the physical meaning of resonance. Okay, this is the the mathematical understanding of resonance, but we have another thing, or we have like real physical implication of the resonance, which is it is going to make our system to fail. Based on this, if our system is like, especially for structural systems, our structural systems needs to be like ductile systems. Okay, if we put it like this, so if our system is ductile system, whenever that there is amplification in the motion like this ductile system is going to like change its stiffness, and then it is going to change the T, which is going to change omega. So the ductile system is going to change the stiffness because some elements are going to fail. This means that the stiffness matrix is going to change, and then T of the system is going to be changed, and consequently omega is going to be changed. This means that this is not going to be our equation, okay, anymore. We're going to, this is for the case of omega bar equal to omega n. So we're going to return back to the original equation. But if our system is brittle system, that's the issue. If our system is brittle, K will not change. So K will not change, and then T will not change, and omega will not change. This means that it is going to make failure here. Okay? Failure will take place. Okay? So in this case, we need our systems to be ductile. Okay? We need our systems to be ductile because here the system, let me put it in here, like if we have, okay, so for ductile system, we are going to find the yielding would take place. So we're going to find yield would take place. Why? Because our omega is going to be changed. Okay? However here for the brittle failure, okay, I will finish now. 1 minute. For the brittle system, it is going to fail. For the brittle system, it is going to like fail. There is a failure here. Failure occurs. So we need our system to be ductile, not brittle. Okay? That's the end of our video. I hope that you have understood it well, and I hope that you go through the two videos together so that you can get the meaning and understanding of this system. Thank you, and see you next time.